Have you ever wondered how a 100-ton machine can soar through the skies at 900 kilometers per hour? Aircraft engines hide secrets that even experienced pilots don't know. In this video, you'll discover exactly how these metal giants convert fuel into the force needed to lift you thousands of feet into the air. Why are modern engines so much quieter compared to older ones? And at the end, I'll share a real-life case that proves this technology is safer than you can imagine. I'm pilot Miguel Santos, and welcome to another video where I'll reveal the best-kept secrets of the engines that keep us flying safely every day. If you're an aviation fan, hit that like button and subscribe with confidence, because today you're going to learn something no one else has told you about airplanes. Let me know in the comments which city you're watching from. I love to know where our followers are. Also, consider becoming a channel member to help us keep growing and to get exclusive content. Let's start with the physics that defy gravity. I'll begin with something you've probably never heard. Aircraft engines work on the exact same principle as letting go of an inflated balloon. Yes, the very same concept that entertains kids is what moves a 500-ton airplane. Newton's third law is the key. For every action, there is an equal and opposite reaction. The engine expels gases backward at an extremely high speed, and as a reaction, the plane is pushed forward. But here comes the fascinating part. The speed of that gas jet is everything. Imagine the difference between gently blowing out a candle and using an industrial blowtorch. The faster those gases escape, the more thrust the engine generates. To achieve this brutal speed, we need to heat the air to extreme temperatures. We're talking over 1500 degrees Celsius, hot enough to melt copper instantly. But before I explain how they reach these temperatures without melting the engine, you need to understand the anatomy of this extraordinary machine. Now imagine the engine as a perfectly organized factory with 4 departments working in perfect sync, 24/7. First department, the compressor. It's like a giant fan with multiple stages that takes in normal air and compresses it to 30 times its original pressure. Notice this crucial detail. The first blades are huge, but they get smaller as you go further in. Why? Because as the air is compressed, it needs less space, just like when you squeeze a sponge. Second department, the combustion chamber. This is where the magic happens. The supercompressed air is mixed with fuel and ignited. It's like having a permanent, controlled explosion inside the engine, but managed down to the millimeter. Third department, the turbine. Superheated gases are ejected from the combustion chamber and spin these special blades. It's like a giant water wheel, but instead of water it uses 1500-degree gases spinning at 15,000 revolutions per minute. Fourth department, the exhaust nozzle. This is where all that power is turned into forward motion, like a tank cannon, but expelling air instead of projectiles. If you're already starting to see why these engines are so incredible, leave a like, because now comes the most clever part of the design. Here is the cool trick. The turbine is connected to the compressor by a special steel shaft. It's a self-powering system once it gets going. The turbine uses some of the energy from the hot gases to drive the compressor, which in turn supplies the air needed to sustain combustion. Now, let's talk about the revolution of silence. The first jet engines had a terrible problem. They made a deafening noise that could be heard for miles. Imagine standing next to 20 chainsaws, running at full blast at the same time. The solution was brilliant. Add a giant fan at the front. These are the turbofan engines we see on all modern commercial aircraft today. This fan does something extraordinary. It moves large amounts of cool air around the hot engine core. It's like having 2 engines in one. The hot core generates power, and the cool fan moves additional air without burning extra fuel. The result is impressive. 80% of the total thrust comes from the fan's cool air, not the hot core. This is more efficient, quieter, and consumes less than half the fuel of older engines. To give you a sense of this improvement, engines from the 60s used twice the fuel to generate the same thrust. It was like comparing a classic car that gets 20 liters per 100 kilometers with a modern hybrid that gets 5. But here comes the most important part that determines whether an asset is safe or dangerous, the most critical moment. What happens when you need to start these metal monsters? They can't start on their own. And here is one of aviation's best-kept secrets. They need an external power unit to get them spinning until they reach the minimum speed to sustain combustion. It's like push-starting a car, but with 20 tons of metal spinning at 10,000 revolutions per minute. The sound of startup is unmistakable. First, you hear the starter motor spinning the blades, then the fuel circulating, and finally, the characteristic roar as the engine becomes self-sufficient. Modern engines have multiple shafts, spinning at different speeds within the same engine. It's like having several engines working in perfect sync, each optimized for its specific function. Here is a fact that impresses me most as a pilot. Each engine can generate the equivalent power of 300 sports cars, but weighs less than 2 cars combined. The power-to-weight ratio is simply extraordinary. If you're enjoying these aviation secrets, subscribe to the channel, because I have much more information that will surprise you. But what happens when something goes wrong in mid-flight? That's the question everyone asks, but few dare to. Let me tell you why you can fly with complete peace of mind. These engines are designed to operate perfectly for decades without failing. Every internal component is engineered to withstand forces that would destroy any car engine in seconds. The turbine blades endure centrifugal forces equivalent to carrying the weight of a small car while spinning at temperatures that would melt most known metals. The materials are extraordinary. Titanium and nickel alloys, high-tech ceramics developed specifically for the aerospace industry, and even single crystal blades grown atom by atom for each critical component. Every engine undergoes tests that include ingesting artificial birds, withstanding hail the size of golf balls, and running for hours with intentionally damaged blades. In 2019, an Air France Airbus A380 lost entire parts of an engine over the Atlantic. The engine partially disintegrated, losing its front cover, but it continued to work long enough for the plane to complete an 8-hour flight and land safely with 500 passengers. No one was injured. This is redundancy and safety engineering taken to the absolute extreme. Now, for the technology of the future. The engines you'll see in the coming years will be even more impressive. Engineers are developing hybrid engines that combine gas turbines with electric motors. Other projects include hydrogen engines that produce zero carbon emissions, only water vapor. Imagine flying in a plane that pollutes less than some cars. Adaptive engines can change their configuration mid-flight, automatically optimizing for each phase: takeoff, cruise, and landing. It's like having 3 different engines in one. Pratt & Whitney is testing engines with blades that adjust to flight conditions, like a bird's wing beat, which changes shape for speed or maneuverability. And for the next generation, companies are investing billions of dollars to make these engines even more efficient. Rolls-Royce is developing engines that consume 25% less fuel than current ones. General Electric is testing ceramic materials that can withstand temperatures 200 degrees higher than today's, which means more power with less weight. Civilian supersonic engines are making a comeback. After decades without commercial supersonic flights, several companies are developing engines that will allow you to fly from New York to London in under 4 hours, without the sonic boom that banned the Concorde. Now you know why those metal tubes under the wings are true masterpieces of modern engineering. They aren't just motors. They are complex systems that turn pure physics into the ability to defy gravity and take us anywhere in the world. The next time you fly, look at the engines with different eyes. You are seeing decades of innovation, billions of dollars in research, and the technology that allows us to cross continents in a few hours more safely than driving a car. Each engine represents the work of thousands of engineers, scientists, and technicians who have dedicated their lives to perfecting every bolt, every blade, and every safety system. If this video has changed your perspective on aviation, leave a like and subscribe for more aviation secrets that no one else tells you. Let me know in the comments. Have you ever noticed how the sound of the engine changes during different phases of the flight? I'll see you on the next flight into the skies of knowledge.